Alright, so in this video I'm going to talk about this result from last time. Talked about the sum n less than x of sum of divisors 2u n chi times sum of divisors 2v n minus k psi over n to the u plus v. And you can see the previous video for some details about exactly what you end up getting and the assumptions on uv, chi, psi, etc. But here I'm going to do it more technically and go into some of the details. So this function v that we talked about last time, which is essentially a generating function for the shifted convolution, this is going to be this completed Eisenstein series. Let me get it exactly. It's going to be me, and then I'm going to write this 1 to mean the Dirichlet character mod 1, chi bar. So this is a Eisenstein series attached to characters in the sense of Young 2019, and I'll write down the Fourier expansion in a second. So it's a product of two of them, and it's going to be symmetric in the two of them. So here, the Fourier expansions are E star 1, say psi bar Zs is going to be equal to, it's going to be n to the s, so this is the level, and it's also the modulus of the character chi and psi, divided by tau of psi, the Gauss sum, and then I'm going to write uppercase lambda for the completed Dirichlet series for psi bar. This is times y to the s, and then you have sum n not equal 0, 2 times the absolute value of n to the 1/2 minus s, sigma 2s minus 1, n psi, again using the usual convention that this means absolute value of n, and then the Whittaker function, y to the 1/2, k of s minus 1/2, 2 pi n y e of nx. And it's also going to be important to know the Fourier expansion at the other cusp. So I will also give this other Fourier expansion psi 1 here without the conjugate, Zs, and this is going to equal to n to the 1 minus s over tau of Gauss sum of psi bar, lambda 2 minus 2s psi bar, y to the 1 minus s plus sum n not equal 0 to absolute value of n to the s minus 1/2 sigma 1 minus 2s n psi, y to the 1/2 k s minus 1/2 2 pi n y e n x. So I hope that I didn't mess up any psis and psi bars or anything like this. You can get this from Young 2019 theorem 4.1. So in case that I copied these down wrong or something. And the reason I write down the second one is because you have this identity that E chi 1, chi 2, and then here sigma sub 0 means the Fricka involution in the case that n is prime. In general, it's a scaling matrix at 0. is equal to e. So you just swap the two characters here. And this is Young 2019. This is section 9.2. And this lets us, this is why I write down both of these. I should also write down the relationship between the completed and non-completed versions. So we have E, the Eisenstein series attached to cusps, E z s psi is equal to n to the minus s, Eisenstein series 1 psi bar, where, okay, zs, and then this is equal to tau of psi bar over lambda 2s psi bar times the completed Eisenstein series. And for the other cusp, E0, Zs psi, this is going to be equal to n to the minus s E psi 1 Zs. And this is just 1 over the completed Dirichlet L function times the completed Eisenstein series. And again, you can get this out of Matt Young's paper. So this is enough stuff to get started to understand this function phi of z. So let's see. So I'm going to focus maybe more on the discrete spectrum here, though I guess I can say a few words about the continuous spectrum. So for the continuous spectrum, so you can pick this regularizing function, which I talked about in the last video. So r of z, in this case, given all these relations that we have, the function r that we're going to get is the following. It's going to be tau of chi psi conjugate over tau chi bar tau psi bar, then completed Riemann zeta function of 1 plus 2u chi bar lambda 1 plus 2v psi bar over lambda 2 plus 2u plus 2v chi psi bar. And then this completed Eisenstein series at 1 plus u plus v. So these were the squiggles from the previous video. And then for the second term, to correct the cusp at 0, you can check that you need the following coefficient. So completed Riemann zeta function at 1 minus 2u chi 1 minus 2v psi divided by completed Riemann zeta completed Dirichlet L function at 2 minus 2u minus 2v chi psi, and then here it's the completed Eisenstein series one chi psi conjugate z u plus v. So again, with these relations that were written down here, you can verify that the Fourier expansion of v minus r at both the cusp infinity and the cusp 0 has no powers of y that have real part more than 1/2. And so what that means is that you can compute these inner products, so the inner product of V minus R with this Eisenstein series at the cusp I infinity. Actually, I will just copy paste this. So let's see. So these are the expressions I end up getting. And for the inner products, again, these just come from ignoring all of the constant terms, and you end up with just the K-Bessel function terms. So then when you put this together with the K-Fourier coefficient, so what we're really looking for, because remember our three steps, right, of one K-Fourier coefficient, two Mellin transform, and three Perron's formula, we can combine 1 and 2, and we can look at this this integral 0 to infinity integral 0 to 1 of, say, 1 over 4 pi I sum over the cusps of gamma naught n, which again we're assuming to be prime, so this is only sum over two things. And then this term in the spectral decomposition, and here you'll have a V minus R with your Eisenstein series at, I'll write it down, lambda chi psi times the Eisenstein series itself, z lambda chi psi d lambda, and then we care about this times e of minus kx y to the s minus 1 dx dy over y. And so this is what you get from combining these two terms. We have expressions for this piece. We need expressions for the kth Fourier coefficient of this this Eisenstein series, right? Because you can think about swapping the order of these two things, right? Just do the integral in x first, right? Because there's no x dependence anywhere but in the what's going to be picking off the kth Fourier coefficient of this Eisenstein series. And again, using these expressions up here, you can do this. And what you end up getting is the following. So doing that, and then taking this Mellin transform in S. So again, in fact, what you want to do is not maybe swap these two, but take this and move it all the way out. So you're doing this integral last. Then, well, what you end up getting from each individual cusp, you end up getting the same thing from both cusps. And the sum of them is the following. At least this is what I get. Hopefully I didn't mess up. So when you bring this out, you see I still have this integral over real part of lambda's 1/2. I've reparameterized that in terms of omega. And you end up getting, in fact, the same contributions from the cusp I infinity and the cusp 0. You can see this maybe just by comparing these two things, right? So if you look at the factors that are present up here but not down here, that's the same as the factors that are present up here but not, or down here but not up here. So you end up getting exactly the same contribution from both, and this is what you end up getting after collecting, after doing the Mellin transform, looking it up in Gradstein and Rizek as we've done before, and collecting the gamma functions and the L functions to form these completed L functions. Okay, we have this expression for the contribution from the continuous spectrum. Let's talk about the contribution from the discrete spectrum. So here I'm going to write, as usual, that my Moss form Fj is equal to sum n not equal 0 of 2 rho j of n y to the 1/2 k I rj 2 pi n y e of nx. And here the idea is you can unfold one of the Eisenstein series of V. So you can write V of z, again using the stuff above, this is lambda 1 plus 2u chi bar over tau chi bar times e I infinity z 1/2 plus u chi, and then I'll leave the other Eisenstein series as the completed Eisenstein series attached to characters. So z 1/2 plus v, and this you can unfold, and what you end up getting is the following. So you get, so here in the inner product, if you can imagine, so this inner product of R with Fj is just going to be 0. So it's this, I should say, if Fj is even and 0 if Fj is odd. So recall that even and odd mean when you apply the Hecke operator at -1, do you get exactly, do you get the same function back, or do you get minus that function back? So R, because it's just a sum of Eisenstein series, right? R was this, right? It's some Eisenstein series and some other Eisenstein series. And the continuous spectrum and the discrete spectrum are orthogonal. This inner product with R is not going to matter. You can completely ignore it. So this means that this inner product of V minus R with Fj is just equal to the inner product of V with Fj. And then for this inner product of V with Fj, you're unfolding this Eisenstein series, and you end up getting this. And this looks asymmetric, right? I mean, there was some arbitrary choice that was made to unfold this Eisenstein series in U instead of the Eisenstein series in V. And then you have this this 1/2 plus U plus V, 1/2 plus U minus V, and a character psi appearing here. But there's no analogous thing for chi. So this is suggesting some asymmetry, but in fact, this implies a functional equation. So this implies a functional equation for, I don't know how you want to write it, for Fj, maybe conjugate. And then well, okay. It's gonna give you, I guess the functional equation implies is, the product of these things, but I'll just write it for this, etc. So you can do it this way. You can also look up the functional equation. So let me see what the reference I had for this was. You can say, so compare with Ivaniech and Kowalski, equation 5.4 and page 132. And that gives you the following functional equation. So, and then there's a similar one for when you have this psi and this chi exchanged, right? I guess what you can do is you can say, apply this to the first term, and then here, if you take this expression and you simultaneously exchange u with v and chi with psi, then the same thing must hold, and so that gives you a functional equation for this second factor. Okay, so so we have this inner product with this Moss form, and now to get the rest of the continuous spectrum, well, we already wrote down what this Fourier expansion of the Moss form was. We basically just stated it, and then we're going to do the same thing. We're just going to look at this triple integral of this double integral times the sum over the Moss forms, and we're going to bring the sum outwards, and this is what we end up getting. The following. So this is, again, just taking the sum over j, bringing it out. For the kth Fourier coefficient, we know what it is. It's just this thing. And then we know what this inner product is because we unfolded this, and then we can take the Mellin transform by just looking it up in Gradstein and Rizek, for example. Okay, so we have this expression, and ultimately, if we look at this quantity, let me see exactly how I defined the quantity. One sec. So let's define L sub k of s. This is going to be this L function associated to shifted convolutions, and it's going to sum n not equals 0 or k, and it's going to be sigma 2u n chi sigma 2v n minus k psi divided by n to the s plus u plus v, and then the asymmetry goes away when you have this hypergeometric function. So now I'll write down what you actually get: s plus u plus v divided by 2, s plus u minus v divided by 2, semicolon s, semicolon 2k over n minus k squared over n squared. So as discussed last time, this thing is approximately 1 for large n, but it's not exactly 1, and you have to deal with it. This comes from looking at this Mellin transform or product of Bessel functions, right? You end up getting this hypergeometric function. So it's kind of crappy, but it's not as bad as if you used a point cavity series, because then you'd have some mess that you don't really have a series expansion for anything. It just sucks. Okay, so we have this function LK, and doing spectral decomposition, we get the following identity. So I'm going to copy paste this because it's pretty big. So this is the identity you end up getting. And so let's break it down. These two terms come from R. These two terms come from so the constant terms of V. Let me do it this way. Right. So in this Dirichlet series, we're excluding 0 and k because for our Fourier expansion of V, when we write it out as a product, there was a term that was coming from this times the kth thing here, and this times the 0th thing here, basically. Here, this is coming from the continuous spectrum, of course. And this part here is the discrete spectrum. So this is what we saw above, right? This is exactly this expression. So now the thing to do is to get into bounding this contribution from the discrete spectrum. The bound for the continuous spectrum is going to be similar, and in these terms, and these are just some gamma functions. These are no problem. So I'll do the discrete spectrum, which is the harder part. So as we saw previously, we've got this bound from Hofstein and Lockhart, which is, it's slightly more precise than what I'm writing here, but if you have the norm of the first Fourier coefficient normalized by the hyperbolic cosine times the norm of the form, this is more or less 1. And to figure out, so that's going to take care of this part right here. Then for the rest, we're going to have to break this up into, well, normally it's 4 pieces, but I will sort of, so the 4 pieces you break it up into are Rj less than 1 plus the imaginary part of U plus the imaginary part of V, right? So this is the part where Rj is near 0, and you can't really use any of these approximations. And there aren't too many of these. You just bound them in sort of a straightforward way. This is no problem. The second part, which I'm going to assume is not, doesn't overlap too much, is going to be when Rj and T, the imaginary part of S, is going to be strictly less than 1. Then you can't really use Stirling's approximation, etc. But you can do some other stuff. It's not, again, not so hard. And then the third and fourth parts are, they get progressively more interesting. So the third part is going to be when Rj is greater than T plus 1. And here you have exponential decay. We saw this when we were talking about the bounding the discrete spectrum for the classical additive divisor problem. When we were talking about Taktich and Vinogradov stuff, we saw that there was exponential decay and then we got some power savings. You can use the same idea here. You don't really need the spectral large sieve at all for this. And part 4, this is going to be the interesting one, and this is the one that I'm going to focus on, is when Rj is less than t minus 1. So when t is bigger than r. This is the tricky part, because here there's no exponential decay. And I'll say, check the Takhtajan and Vinogradov video. So for how you end up with exponential decay here but not here. And what you end up getting is, and I will symmetrize it, because here you see that there's an asymmetry in U and V, and I don't really like that. So I'm going to write it as, I'm just going to square it and do it both ways in each piece. So you end up getting this thing, and this is a product over all 8 sign combinations here. This is just taking this thing and just doing it again with uv chi psi interchanged, right? Okay, and now let's start by using Stirling's formula. That's going to be the easy part. So the easy part is handle gamma functions with Stirling's formula. So you can check just by working it out that the exponential part is 1 in Stirling's approximation, and this uses our assumption that r is less than t. And then the polynomial part is, I'm going to ignore a lot of constants here, right? So here I'm going to ignore all these constants that, say, depend on the level n, the shift k, u, and v, and I'll say that this is going to be less than, and if you go and track it carefully, it's going to be, well, not so carefully, it's quite straightforward, t to the 3 minus 2 sigma as your t power. That comes from this gamma here, that this is sigma minus 1/2, and then if you look at these 4 things in the denominator, again, ignoring the UV dependence, assuming that t is very large relative to UV, the exponents, here are the real parts, they all cancel out, and we just get a t to the sigma over 2 minus 1/2, then the 4th power, so it's sigma to the 2 sigma minus 2, and then you sort of rearrange and you square it, and you get this power. Then for these 2 factors right here, this gives you a t plus rj to the sigma minus 3/2 times t minus rj to the sigma minus 3/2. Again, just this is the real part is this is assuming Selberg eigenvalue conjecture. And this is assuming Selberg for simplicity. you could do this without assuming the Selberg eigenvalue conjecture, and then you get, maybe like a theta, which represents the best progress towards the Selberg eigenvalue conjecture. I think it'd be 7/64ths as of the time of this video in this exponent. But anyway, I'm going to assume the Selberg eigenvalue conjecture, just so I can write it this way. And then finally, the power of r that you get from these four things, well, you see that the real part of this, the real part of this is going to be 1/4, and then you have the plus minus UVs, but because you're taking product over all four sign combinations, these all end up canceling out, and T, or Rj, we're assuming, is much larger than the imaginary parts in U and V. So you can collapse all of those factors into one, and you just have an Rj to the 1/4 minus 1/2, so minus 1/4, and then you take that to the 8th power, so you can get an Rj to the minus 2 here. And that's what you're going to get from Stirling's approximation, is you're going to get this part as your polynomial thing. So what we need to do is, this means that we need to bound and it's going to be the sum for Rj less than, here it's going to be t minus 1, but you could use t, that's the same, and then it's going to be this polynomial part, so t to the 3 minus 2 sigma t plus Rj to the sigma minus 3/2 t minus Rj to the sigma minus 3/2 Rj, and then you could do minus 2 here, you could do minus 2 plus epsilon coming from this bound if you like, but it sort of comes down to the same thing. And then you still have your L functions. So your L functions are going to be, right, so let's look at this. We have these 4 L functions right here. So that's going to be L to the L of 1/2 plus U plus V Fj bar, L 1/2 plus U minus V psi cross Fj bar, L 1/2 minus U plus V chi times Fj bar, and then L 1/2 minus U minus V chi psi Fj bar. Okay, and the way to do this is using Cauchy-Schwarz. So when you use Cauchy-Schwarz, well, really we're interested in this quantity square root of, right? Because we had the square of this thing, and we want to know what the square root of this quantity is. Because this was just for one specific fj, this is what it was, and we're summing over j, and we were summing over the square root of these things. And so using Cauchy-Schwarz, you get that this thing is less than the sum, and I'm just going to write Rj less than, well, I guess for this term, I should be a bit careful, and I should continue to say t minus 1, just to make sure none of these are dividing by 0, of, okay, the same thing, t 3 minus 2 sigma t plus Rj to the sigma minus 3/2 t minus Rj to the sigma minus 3/2 Rj to the minus 2, and then it's going to be this square root of, and then times the sum rj less than t minus 1, and then the absolute value of all of our L functions. So maybe I'll just copy paste this. So here I'm going to put just these absolute values. Sorry for, I would want to just indicate that I'm separating all of them. And then this is going to be this to the 1/2. So this is from Cauchy-Schwarz. And then you can Cauchy-Schwarz again each of these things individually. So this, well, okay, let's look at what this is, right? So if we just assume that all of these are about t, what do we get? We end up getting t to the 3 minus 2 sigma plus sigma minus 3/2 plus sigma minus 3/2. So that's t to the 0 from these three things. And then assuming that r is, so it's r to the minus 2, and recall the Weil law that there are about r eigenvalues between t and t plus 1. So what that means is that this first thing is just going to be t to the epsilon. And then for these individual L functions, we end up getting the sum rj less than t minus 1 of L of L of 1/2 plus u plus v fj conjugate. And this is going to be to the 4th power after we Cauchy-Schwarz each individual piece. And this is going to be all to the 1/8. And then times same thing, but with the other 3 L functions, right, with the different combinations of signs and characters. And they'll all be similar. So, okay, so we need to understand how each of those are going. And for those, we're going to need some additional machinery. So there's this thing called the approximate functional equation. So the approximate functional equation is the following. You have this L function, and I'll give Iwaniec-Kowalski theorem 5.3 for this. So if you have this L function, LFS, which is a pretty generic L function for Iwaniec-Kowalski, this is equal to sum over n of, and now they write, I'm going to write an over n to the s, so this is kind of like their Dirichlet series, and then they've got some function v, which, okay, it's some nice smooth function, whatever. You can think of this as being an exponential function, e to the minus x or something. And then there's some arbitrary parameter capital X, and then there's the square root q, which is the conductor of this L function. And then here in the numerator you have this n, which is what you're summing over. And then you have a second term, which is given by the root number of f times the conductor of f to the 1/2 minus s. And so this should be the same. In their notation, they write q and qf here, but these are the same quantity. And then you have these gamma functions. This is a product of, so the gamma factors in the functional equation. F1 minus S over gamma Fs, and then you have the same sort of Dirichlet series. Here they have an conjugate over n to the 1 minus s, and then they have v 1 minus s, and then here they have nx over square root q, and then they have this remainder term r, which is 0 for us. It's 0 if your function is holomorphic. So here q is the conductor of L. Vs is smooth and of rapid decay. And if you want to know more about this, check Ivanovich and Kowalski, the next statement, so proposition 5.4, which, when you care about things other than the t dependence, this can be a little bit tricky. But if you care about only the t dependence, you really, it decays extremely rapidly. You don't have to worry about it. And the point is that it's kind of a fixed function, especially, and think about taking x equals 1 here. So, as long as n is significantly bigger than the conductor of f, then you're truncating the sum, right? That's the point of this function v. It's to truncate the sum at about the square root of the conductor. So truncates the sum at n is about square root q, and ish, roughly, close enough. And then here, gamma is gamma factors. In the functional equation. So you don't really have to worry about them too much. So what you can look up is that the conductor of L S, and then I'll write star here to mean any of these 4 things, right? So it's either f, or it's psi times f, or it's chi times f, or it's chi psi times f. Or I guess I'll write star to mean any of the trivial character psi chi or chi psi. So this times fj bar is about rj squared, maybe with absolute values. And what that means, right, with this approximate functional equation is that, so also we're looking at the 4th power of this. So what that means is that this L function, Ls star times fj conjugate squared, is estimated by a sum of length, and then here it's going to be the square root of the square of this quantity, because this approximate functional equation, again, think about taking x as 1, then because v is some fixed function, then when n is significantly larger than the square root of the conductor, then you these terms don't contribute. And the square of this L function, I mean, remember we saw that you could, if you had the sum sigma w n times alpha j, so the Hecke eigenvalue of n over n to the s, we found that this was equal to something like L s fj L, maybe this is with a character, right? This is L s chi times fj divided by L 2s chi, I think. Something like this, right? So you can see that when you have the square of this L function, then you end up getting another L function in Dirichlet series, and the coefficients are about the same, but you can use this general theory of L functions that you can read about in Wojciech-Kowalski chapter 5 to say that the conductor of the square is going to be the square of the conductor. So this function, this L function, is going to have conductor that is the square of rj squared, so rj to the 4, and you're truncating the sum at the square root of that conductor, so you're truncating that sum at rj squared. Now, the Dirichlet series Ls star times fj, say conjugate squared, let's just call the Dirichlet coefficients b, right? So bn over n to the s, that's going to be sum over n, and you can find that bn is less than rj to the epsilon. As a reference for this, not exactly this fact, but a similar fact we can reason. It's basically this idea, but the way that's written out more carefully is Jeff Hofstein and Min Lee in their 2020 archive preprint. And it's going to be equation 3.75. You can reason the same way and get this bound. And so these Dirichlet coefficients are all basically 1. And now the key idea is, so taking all of this together, what we're basically applying the approximate functional equation to this term, we find the following, that L s star times fj conjugate squared is less than some n from 1 to, not 1 to infinity, but 1 to rj squared of, and now it's going to be n to the minus sigma, right? That's going to be the real part of n to the s, and then you have plus, and now for the coefficient in front, this root number is going to be absolute value 1. This is not going to matter for us, and then you have this analytic conductor here. So this analytic conductor is going to be rj to the 2 minus 4 sigma, right? Because it's 1/2 minus s of rj to the 4, and then you have an n to the 1 minus sigma here, and this is multiplying your Dirichlet coefficient bn, right? You can see that Bn and Bn conjugate, I mean, they're about the same size. This is all just less than less than. Now, so we've got this this approximation, and we can think about putting this in to this sum right here. So we're looking at the sum Rj less than t of sum n from 1 to Rj squared of n to the minus sigma plus Rj to the 2 minus 4 sigma n to the 1 minus sigma times Bn, right? This is what we're looking to this absolute value squared, right? This is what we're looking to approximate here, because this is, I mean, okay, it's the fourth power here. That's the absolute value squared of the square. And how do we estimate this? Well, this is where the spectral large sieve comes in. So let me copy paste Hofstein and Lee, that same archive preprint that they have. So this is again Hofstein Lee 2020 archive, and you can also see Ivanovich Kowalski. This is, they say it is theorem 7.24. Right, there's a whole bunch of stuff like this that does it. So here they've got this slightly different normalization than we do, but in terms of what these AMs represent. But essentially, this is what's going on. Well, the way I guess you can see this is that this row J, this has a row 1 in it, and that's going to be canceled out by this e to the minus 2 pi rj, right, using this result of Hofstein-Lockhart. From, I believe it is 1994. Right? You can see that these two things end up roughly canceling out, and then assuming the Selberg eigenvalue conjecture, we're left with just AM as the size. So what does this end up giving? Well, this means that here this implies that this is less than. So here they have rj less than t to the c. Here we just have rj less than t, so it's going to be rj less than t to the 2 plus epsilon, and then it's sum n from 1, and I'm going to take it until t squared because rj is less than t, so I'm just going to take this m to be t. So this m here, sorry, I'll take it to be, I'll take m to be t squared here, and so here we have a level dependence, but like I said, I'm not going to track anything other than the t dependence. So this whole term is t to the 2, and then here we have t to the epsilon coming from this. And then this absolute value squared of the RAM is this thing, right? This whole thing that we're summing up. So this is going to be n to the minus sigma plus, and then again I'll replace r with t because r is less than t. It's going to be t to the 2 minus 4 sigma n to the sigma minus 1. Oops, so this should be sigma minus 1 here, shouldn't it? Yeah. My bad. Right, because it's minus 1 minus sigma. I bet I made the same mistake here. Yep. It's going to be sigma minus 1. Did I make it anywhere else? Okay. So it's this quantity squared, and then we have this b that's floating around, but we said previously that this is rj to the epsilon, and we already have a t to the epsilon here, so I'm just going to omit this b here. And now going term by term, so let's look at just this first term squared. This is going to be n to the minus 2 sigma. We sum it, so it's going to be n to the 1 minus 2 sigma. So put in t squared, so it's going to be n to the or t to the 2 minus 4 sigma. So it's t to the 2 plus epsilon times t to the 2 minus 4 sigma, and then plus epsilon for good luck. And then say we square the second term and we work it out, I think we get a 1 here, and then the cross term also is something smaller than both. So this is what we end up getting. And cool, okay, so this is good news, right? So what was this? This was, so this was a lower bound, if we backtrack, for the sum rj less than t minus 1 of this L function, Ls star times fj squared, absolute value squared, was bounded below by this, right? So now let's go look at, I should say also that this is for sigma between 0 and 1. This is all for the critical strip. So let's take this approximation that we have, or this upper bound we have, and plug it into our bound for the continuous spectrum, right? Because remember, all of this is about trying to bound this in this fourth case of rj less than t minus 1. And we had used Cauchy-Schwarz to break it up into these pieces. We found that the part coming from Stirling's formula, which is the t to the epsilon, and then we have 4 of these pieces, all to the 1 over 8. And so what do we end up getting? Well, this implies that, let's see, that I don't know how to write this, the discrete spectrum contribution is less than, well, what are we going to get? Well, our sigmas here, we had 1/2 plus u plus v, 1/2 plus u minus v, 1/2 minus u plus v, and 1/2 minus u minus v. So, okay, let's just assume that u and v both have real part that's strictly positive. Then for this term, let's say the real parts are ordered, where the real part of u is greater than the real part of v, which is greater than 0. So this term is going to contribute, this term is going to contribute, but for this one, sorry, not contribute, but for those terms, this part here, this t to the 2 minus 4 sigma, those are going to be smaller than just 1, right? Because we're subtracting off, sigma is going to be greater than 1/2. But then for the other two terms, we're going to have this factor be the dominant one. So we had this to the 1 over 8 to the 4. So we end up getting that this is all going to be equal to t, so this 2 to the 4 to the 1 over 8, that's a 1, and then plus, so when we break it down case by case, we see that we can always write this as the real part of u plus v plus the absolute value of the real part of u minus v, right? That's always going to capture the fact that for two of these terms, it's the one that contributes, and for the other two terms, it is these things that contribute. And then this is going to be divided by 2, because it's this, again, to the 4th power to the 1 over 8, and then we still have our epsilon coming from this, also coming from our epsilon right here, but also coming from this part right here, where we can't forget about this r to the epsilon from this. So this ends up giving us this bound on the discrete spectrum contribution. So when I say the discrete spectrum contribution, what I mean is this quantity square root, right? So maybe I'll say the integral 0 to infinity, integral 0 to 1 of this sum over j of v fj over fj, 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 z, and then it's going to be e of minus kx dx, and then was there a y to the s here? Yeah, y to the s minus 1. Right, this is the quantity with the sum over j that is bounded by this. And so this is what is known as the spectral large sieve. And saying that it's the spectral large sieve, it's really this thing. This is the spectral large sieve. Right? It's sort of this idea that you can take the sum over eigenvalues and take some polynomial in the coefficients, and then you can bound it over a sum of the coefficients. I mean, maybe it's the idea, maybe it's the specific formula, but anyway, this combination of techniques, and crucially, this fact is what gives you the spectral large sieve. And people often say that this is Lindelof hypothesis on average. And what does this mean? Well, if we think about the Lindelof hypothesis for these L functions, right? So we have L of 1/2 plus minus u plus minus v something times, something times fj bar. Right, this has this L function s to 1 minus s, and we have this picture for the exponent where, because of the functional equation, we're doing this, right? So this is going to be 1/2, 1, 0. And the Lindelof hypothesis is that this growth is t to the epsilon for this region. And then if the growth here is going to be it's going to be the conductor, the analytic conductor here, right? So it's going to be RJ. It's going to be RJ squared. Okay, well, it's going to be something. And the point is that if you look at the expression that we end up getting here, and you were to apply the Lindelof hypothesis to all of these individually, just pretend that they satisfy the Lindelof hypothesis. Well, again, for 2 of these 4, the argument here would have real part at least 1/2, And so you could just replace them with a t to the epsilon. That's basically like saying, for all of these things, you can replace with a t to the epsilon. Though, I guess, sorry, that's not true because so this sum anyway. Okay, you have this. Yes, that is true, right? You could replace the two of these with a t to the epsilon, and then you get a t squared, but then you take 1/8. So when you do that for all four of them, you're gonna get your t to the 1 right here. But then for two of the four factors, you can't replace them with t to the epsilon. You need to replace with something bigger. You need to replace with whatever you get along this line. And this is going to give you this, so I think this must be t, right? I think it's t. And that's going to give you these things, because then you're square rooting at the end of the day, because in this thing, this was the square of this thing, of the right-hand side, just to symmetrize it. So if one of these is t to the real part of u plus v, then your oh, I see. No, it's going to be t squared, right? And then it's going down with a slope that's twice this, and then you're taking the 8th root, something like this. Anyway, when you work it out, this is what you get. So basically, if you pretend that all of these things satisfy the Lindelof hypothesis, then you would find that you wouldn't need to do the spectral large sieve. You could just go term by term and get exactly the same bound. Where two of the four terms, you just get t to the epsilon, and two of the four terms, you have t to the real part of u plus v, times 1/2 or something, or maybe 2. Okay.